Hunter, that's cool. It's good. Okay, still short a bunch. There we go. There we go. People are popping in.
When advertising on YouTube, I know that making an authentic video with a clear call to action is the key to getting results.
Hello, friends. If I look sad, it's because I am sad. All right, so, I mean, I often have large breaks in my upload schedule on my channel, but usually that's because I have anxiety problems or I'm not sleeping well. It's usually problems based on my own well-being and personal situation. However, you may have noticed I've had a little bit of time off on the channel, and there's a funny reason behind that. So I got another YouTube strike.
Okay, well,
now I can't upload for a week. I mean, maybe
before we depart, I'll do
the
attendance at the
restriction. I've been
end.
waiting
It's
like
brutal
3
to do
days.
attendance this way.
You may have been following my
good to see you
memes
again.
on Twitter.
Let's see
Now,
chat.
I'm only
Good
here
morning,
to
good
update
morning,
you. This
everybody.
is
Just
not starting
checking the
some
chat.
crusade on YouTube.
Yeah, I'm going to address that.
I'm a signed YouTube streamer.
Yesterday,
I love YouTube.
just
That
to
sounded
start
sarcastic,
here,
but it
okay?
is true. YouTube is the
so
best. They
good
don't
to see you.
have an
Welcome
easy
back.
job. But what happened was... basically, one of my
I'm going to
TikTok
just address
videos
yesterday.
from 4 or 5 months ago,
I'd said, and I get it. Pardon me, if you were in class with me, I would tease you and maybe hit you with something or throw something at you.
No kid got seriously hurt. There's no lasting damage.
Past Monday, I said that Mondays were going to be treated as optional days.
Dangerous activity
that,
by a child.
Office hour days. If you wanted to come in and meet with me and or had a question, any of that, I was going to just wait to receive emails from people. If they wanted to meet, I was going to leave it up to the people saying, yeah, I want to meet on Monday. Can we take a few minutes to go over this or that? And I didn't receive any of that, so I was going to kind of leave Monday off. But I got a lot of people. I answered more emails yesterday than I think I have for students in any one single day. I probably had about 25, 30 emails of people like, hey, I couldn't get in. My student view didn't work. So I had intended to just kind of like let it be an office hour day, and if people needed me to check in. But I had kind of noticed people were emailing me, so I was trying to get into my Zoom as well, and I couldn't. They changed. There was another update to Zoom for staff over the weekend, and that changed another protocol for us. And we did not get the change of the protocol until 11:40 yesterday. So what I thought were my meeting schedules were screwed up, and they weren't there, and they weren't highlighting, they weren't turning green. The system changed once again. And so what I'm going to do, though, is I am going to, just because I don't want to create confusion on yours, and I want everybody to listen and connect with this, is that Mondays are truly optional, but I'm going to show up every Monday. Okay, I will just do due diligence and show up Monday and say, listen, I've got 2 minutes for you. There's the weekly outlook. This is what we're focused on this week. Any questions, concerns, stick around. If you don't have anything like that, you do not have to show up on Mondays. Okay? A lot of that, and it's hard for you guys to understand that, a lot of that is me trying to treat you with like adults and put the onus of responsibility on you and saying, okay, hey, listen, if you're sitting there and you tell me that you're good and you own this and you don't need Mondays, good for you. In college, we go to class 2 days a week, 3 days a week. You don't need to go every day. So a lot of that was kind of done in that respect. I would rather take things to the next level and be like, hey, let's treat them like 19-year-olds. So freshmen in college, rather than treat them like 14-year-old, like they're in 8th grade. Okay, so it's better for me, it's better for you. Okay, so I'll still show up on Mondays. It seemed like there was a need there, and maybe people just love seeing my face. Mr. Vista, make me happy. So I will show up on Mondays, okay? All right, so that's that. Don't worry about it. Nobody got marked attendance. And the truth of the matter is, I'm going to say it, I suck at attendance anyway right now. It's brutal to take attendance this way when it's a name. And not like I can look around a room normally. I'm like, oh, okay, Chris isn't here. So-and-so's not here. Great. I know it. Okay. It's tough. All right. So let's share that screen and see what we're going to do today. All I really asked you to do was the principles of engineering, things to do. I had just previously asked, let's go back to that. I just posted that slide, just PowerPoint, take a look at it. I would imagine most of you probably didn't look at it. Maybe some of you did. That's okay. Either way, we're going to go into it and talk about that now. But all we're doing today is really going to talk about that. And I want to be very careful. My DE class, it's tough. It's a challenging class, very hard class. Hopefully, if you're able to take it next year, I recruit you and take that class. Very, very, very good class. And it's tough. It's very, very challenging in the beginning. So I lost my train of thought with that. I talked to them today for 45 minutes, and I'm like, I'm sorry I did that to you. But I try to make it interesting, exciting, but that's a little bit longer than the human brain can go when it's, trying to be attentive to something. So it may be that we get through a certain point today. I just introduce those variables and stop. And I might post, it just depends what the vibe is and how we feel at the end of today. And I'm just, asking for your direct input. So we'll see if we get to the practice problems. Your asynchronous work tomorrow may be practice problems. It may not be. Let's see how this goes. Okay. So without further ado, I'm going to just jump back to Classroom where I had this posted, and you'll see that's the PowerPoint. Okay. I already logged in today, so it shouldn't prompt me to log in again. All right. So you're going to notice right away that I keep calling this drivetrain systems, because I want to pull it all together systemically. So let's just talk about, again, we're in Unit 1, Mechanical Engineering. We talked about simple mechanisms. We got, 4 formulas. We got this idea of mechanical advantage, which is important. I want to use that as a point of comparison. So we had this mechanical advantage, and then we had these variables. We had an effort side, a resistance side, and a force and a distance. Okay. We had this thing called static equilibrium. Well, none of that really exists here. But the reality is that when we talk about in mechanical engineering, these systems are as essential as the simple mechanisms. But the reality is that if you look around the world, everything's compound machines, and it's a marriage of these. adaptations of these, iterations of
After
these.
using TubeCarm
Okay,
for
putting this
literally just
with
3
this
months.
and making this new thing. There's all kinds of other
They helped me
mechanisms that
go-
we don't even talk in a class. Talk about. So this is not the end all be all list of all the mechanisms that are used in engineering, but the reality is you can make a lot of different things from the basic ones. So that's why we're focusing on these. Obviously, another common group, the simple mechanisms are just very common and easy to understand. So this group is another
After
thing that we
using
can relate
TubeCarm
to very
for
easily. The
literally just 3
variables are very
months.
straightforward. So it's a great introductory starting point. Okay. So very same in the world of mechanical engineering, but now we're just talking about a little bit of different systems. But the biggest thing is what I wanted, the point of comparison I was referring to is simple mechanisms over here on our left have mechanical advantage. I can't write, right? Mechanical advantage. Drivetrains, which I'm calling all the drivetrain systems, you'll understand why I lump them into drivetrains, drive systems, as there's a kind of a rotational movement actions. They're always driving something. They just look physically different, okay? They create something called gear ratio. It's a little wordy there. The simple mechanisms and compound machines create mechanical advantage. The drivetrains create gear ratio. And the same thing is true. The greater the mechanical advantage, the better off we are. The greater the gear ratio, the better we are. And it's similar. We've got 4 variables, and we'll look at those 4 variables. All 4 of those systems, generally speaking, have all 4 of the variables. We're going to be looking at how fast something rotates, how big the diameter of something is, maybe how many teeth it has on it, and then we'll also talk about torque, rotational speed. So there's several different variables in there we'll talk about, okay? This is a great little slide. Sometimes you read this stuff and it gets wordy, so it helps to put it. They provide a movement. Yeah, they can change direction. Yeah, they can change the speed of something, okay? But the reality is that these rotational systems create movement, which ultimately leads to motation. I was going to say 2 words, motion or rotation. Motation. That's a new word, motation. Motion or rotation, okay? So, you can look at those 3 things right there. What do we have? And let's just get some context on what this is. This is a gear system more than likely in a car, okay? Probably, and if you look at it, probably a 1, 2, 3, 4, 5 speed car, 5 different gears. That's probably the transmission on a car. I don't know exactly because they can look a lot of different things. It might be a transmission for a truck or whatever, but more than likely transmission for your everyday vehicle. And there's 5 different gears on it. And if you know anything about cars, like a stick shift car, there's generally 5 gears plus reverse. And most of our cars, if you can pay attention to the movement of the car, usually has 5 gears. Maybe a faster car, a more powerful car might have a 6th, okay? Something like this, tough for you to relate to. This is more than likely the underside of a lawnmower. Okay, very, very common. And what we've got now, this is where it's a little bit confusing. We've got this. Here's the gears. Let's look at these in orders too with our terms up top. Gears, fine. Okay, there's gears. There's teeth meshing together. Let me grab something. Okay, just simple nice thing to show you real quick. Just easier. Okay, so we got the gears on the left, and again, what are we talking about? We got 2 gears here with these little teeth on them, right? And those gears mesh together, and we can rotate them. Okay, and it's actually really interesting. As one rotates one way, one is rotating clockwise. It forces the other one to rotate the other way. So there's kind of the idea of changing direction of rotation. If one is rotating clockwise, one is rotating counterclockwise. We'll look at all that stuff. And here's a sprocket and chain. So sprocket looks different, bigger teeth on it, but why are those teeth bigger? Because now they do not mesh that way. That's not good. That's not good mechanics. Look at all the play in there. Those things will slip and break. We attach them just like we do on your bike, sprocket and chain. So now there's a sprocket around there, and it goes to another sprocket. Again, we can create mechanical advantage. And just think real quick, not mechanical advantage. We change gear ratio to manipulate the work that we were able to do. And think about your bicycle. You want to go uphill or you want to go downhill. You're changing these ratios. You're changing gear ratio. You maybe I'm shifting gears. You're changing gear ratio on a sprocket and chain system, okay? And making it easier or harder. We'll talk about that. So that's more than likely a lawnmower pulley system. So this is maybe connected to a motor, and that motor is spinning, and then that is what spins the blade. That's the magic of pulley systems as opposed to a pulley like this, right? Motor pulleys, which you're going to continue to refer to me, I wish they would put that in front of there, because pulleys are a simple mechanism, right? But a motor pulley, okay, or a drive pulley, we can talk about it in those two ways. In this case, where there's that pulley-like thing, but there's a belt, okay? There's some form of rubber belt between them, so that's different. Gears are pretty straightforward, but then, hey, Risto, you said this isn't simple mechanisms. If Project Lead the Way is bad here, they should either put drive pulleys or motor pulleys. Drive pulleys would be best to me because they're driving some form of action. But maybe this pulley is connected to a motor, just a simple motor that's spinning. Okay, fine, we get power and the engine's going, but what are we going to use? We're going to use that power to do something else, and that's spin a lawnmower blade. So that's very, very common, very, very common in your snowblower. You've got a motor that runs and spins the engine, and then I pull an apparatus, and what that does is a lot of times that apparatus is putting tension on this belt. We put a little bit of tension on there, pull on it a little bit, and it gets tight, and it starts to grab something. It pulls on it, okay? It's a really simple mechanism. You're actually using a first-class lever to activate your snowblower or the blade on your lawnmower or the wheels driving forward. If you ever have to cut the grass, you want to go forward, you grab the little mechanism, and all of a sudden it goes forward. What are you doing? You're engaging this pulley. You're activating that pulley, or you're basically pulling right here with a wire. It's very basic description. Put a little bit of tension on there, and it starts to, there's a little bit of tension, then it'll grab that one. So motor pulleys are important. And then lastly, we just talked about sprocket and chain, small little one there with your bicycle, okay? Just real quick, gears mesh teeth to teeth, right? So that's all we're saying here. We got a nice little picture in the bottom, gears mesh teeth to teeth, okay? Very, very important that the engineering, the manufacturing of that is extremely accurate. That what we refer to as pitch, oh shoot, I didn't go over the screw. I was gonna go over the screw. I'll go over the screw on Thursday. I had a note to do and I didn't, but there's something called pitch. Pitch is the space between those, and there's a term with pitch that has to do with the screw. That's why it popped in my head. So that's teeth to teeth, right? Very, very important that they're mechanically made, engineered very nice, okay? They create motion and they transfer, energy, okay? I can transfer, if this one's spinning, I can spin to this one. Okay, we'll look more specifically at them, okay? Some general things, okay? And these are great images because it just talked about what I said. So let's look at the blue one. Let's look at its rotation. The blue one is definitely rotating clockwise down this way, right? If this is the top of the clock, it's rotating this way, right? Well, what's that causing the next gear? The gear that's mating. This is the mating gear. They're mating to each other, right? Teeth. So that's one of the things we'll say about gears. Gears can control direction. I can control direction and rotation. If I just want something to spin, but my motor is spinning this way and I need to change the direction, there's actually two ways we can do that. You can do that with electronics. Electrically, you could change polarity and wire it backwards. That would force something electronically to wire, but mechanically, we could do that with gear direction, okay? And if I needed to, for some reason, get back to that original rotation for whatever it may be, all I do is put another gear on there. I got it, for some reason, everything's got to rotate clockwise, okay? There's this term of pitch is the idea that the spacing between the gears is always the same, that they fit together real nice, okay? This is intuitive and it makes sense. So I just look at these things real quick and just want to talk through them. The RPM, it's a new acronym. You might see it in your car. If you're driving a car yet, some of you may or not know what it means. RPM is rotations per minute, or revolutions. Technically, it's usually most revolutions per minute. How many times something revolves around per minute? Very common unit of measure in speed and velocity, okay, for rotational objects. Okay, so the RPM of a larger gear is always slower than the RPM of a smaller gear. And think about that. If these were both gears, this one, the bigger one, would take longer to rotate than the smaller one. So that's an important concept because the bigger something is, the slower it goes. So when we want a mechanical system to go fast, we actually have to use a small gear. And I want you to start looking at your bicycle. Really start looking at your bicycle. You change those gears and wow, I'm manipulating gear ratio. And my output is coming from the smallest gear. And that's why I'm able to spin my wheels really fast, because my output gear is the smallest one. We'll get there, okay? So it makes sense that the bigger the gear, the bigger the diameter, the slower. Very intuitive. It takes longer for that to rotate than it does because this is smaller, okay? So the general idea with rotational objects is the bigger they are, we use them for torque. We get a lot of work. That's big, it's strong. And when it rotates, it can create a lot of energy. This is small, it just goes fast, okay? So it's a very, very important concept, okay? Just general concept. The larger they are, we use those for torque, okay? And the smaller, we use those for speed, relatively speaking. Iterations, adaptations all over the place, depending on the engineering, okay? Gears that lock together is making here, right? This is a bigger gear, this is a smaller gear, but guess what? They've got a central shaft. There's one shaft that goes through them, and if that shaft is spinning at 30 times per minute, this one's gonna go 30 times per minute, that one's gonna go 30 times per minute, okay? This is a compound gear. When the gears are stacked in front of one another, we refer to that as a compound gear. You'll see more examples. So here's gear ratio. When we talk about gear ratio, remember the difference. We had simple mechanisms in there. We're trying to create mechanical advantage. Fine. We use those systems as engineers to get work done. The other systems, another one of the systems that we use are drivetrains, okay, to get work done. It's just another way for engineers to get work done mechanically, right? We have 4 variables. They're right there on the screen in front of you, okay? So, and the variables, the letters that we use for the variables are very, very easy, okay? So you just gotta make a little association with them. So we can look at the number of teeth. So when I look at the sprocket and chain, I can decipher gear ratio through these 4 variables. If I compared the number of teeth on this one to this one, I could determine a gear ratio really quickly looking at it. I can count the number of teeth. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Okay, 1, 2, 3, 4, 5, 6. Fine. I've got it, my teeth count. We'll use them in a minute. Diameter. Okay. Oh, it's telling me. Doesn't give us our diameter symbol, but it's telling me that this diameter is 4 inches across. This one's 2 inches across. Important. Okay. But I can use that as a variable to compare gear ratio. This one's tough because you will generally, when you see it written in a mathematical equation, you'll see it later on, it will be changed. And I think they use the Greek letter, the Greek version, okay? But angular velocity, if I was to annotate here, sorry, this would be our RPM. RPM, revolutions per minute is our common unit of measure, and there you see it there, okay? Revolutions per minute and RPM. That's the one. And when we talk about angular velocity, this is where you get into the deep physics of things. Angular velocity, it's like why they call it angular velocity with it being rotation has to do with some aspect of physics, tangential lines, but that's just what they refer to it here as. That's our rotation, RPM, speed, okay? And then the last one is torque. And when you see torque, we're starting to see that, look at what we know there. Hey, you know what, torque, that's that moment. I can tell it's a moment because it's a force and a distance. Look at that. Torque, a unit of measure for force, a force applied to something. Okay, I can apply 80 foot-pounds of torque to this. I can apply 40 pounds of torque to this with a wrench, okay? So those are our 4 variables. We can look at number of teeth on a system. We can look at the diameter system. We can look at the rotational speed of it, and we can look at the torque. Now, right away, when you look at this up here, they didn't put any of the torques. Well, they're written down there, but they're going to be written in your word problem. The last thing that is important, in order to set these up, you have to know one last thing, and it's right here. So those 4 variables, in order to set the equations up, we need a couple things. The 4 variables. We need to know, the next thing we need to know is what's output and what's input. And the last thing we need to know is the formulas. We haven't done the formulas yet. Okay, we'll see on the next slide. So there's the 4 variables. I can establish gear ratio, identify it by setting up equations with those, but I also need to know what's the output over the input. Here's why. So here we go, just real quick, looking at the slide. Here's the number of teeth. The blue one is what we're referring to as the output gear. And this one, the red one's the input gear. Now, what does that mean? If I had a motor, the motor would be connected to this one. Or if I had a hand crank, I was hand cranking this one. That would be the input to this output. So say, that I'm cranking this. Probably the easiest mechanism I can think of like that in your everyday house is an egg beater, right? The egg beater, the handle, which is a simple mechanism, a wheel and axle, that translates down. I think it's a screw that goes into a gear. So, right, thinking about something just you take for granted. Oh my God, that's actually a wheel and axle crank with a screw that I believe that transfers its energy to a gear, right? Okay. So the input, then the output would be the gear that's driving the egg beaters. There's a lot going on there with changing of direction of energy, okay, for such a simple device. Cool. I want to look at one more a little bit. Think about it, okay? So we've got diameters established, rotational speeds, and torque, okay? So let's look at how we set these up. So here's what's important is that we have this basic idea that gear ratio, just like mechanical advantage, is always in relation to a 1. I can write, guys, we all know this. Sometimes it helps to see it, but I could write this the same way, GR:1. That's the same thing, right? 2 to 1, right, is exactly the same as 2 over 1. Same thing, okay? So just know that those are all equal to each other, okay? So gear ratio, just like mechanical advantage, we express it as a ratio for what am I getting out to what am I putting in. That's basically what that says. For every 1 I put in of something, right? Just generally, very generic, for all that 1 effort I put in, I get that amount of effort out, okay? So that's all it's showing is what I'm getting out for what I'm putting in. Now, there's those 4 variables, number of teeth, diameter, there's that, and I believe this is the Greek. I'll have to look that up. That is definitely a Greek lowercase letter, and I'll look up, I will know for sure. I might be for V, okay? Somebody wants to Google that up on the side real quick, and there's your tau. There's the Greek letter T, okay? So oftentimes you see that. It's a nice thing about this class. You see the Greek alphabet come by. Why? Because they're universal across the planet, okay? That's why. Okay, universal engineering is a universal language, particularly through the SI system. Okay, so here's our 4 variables, and now I'm going to give you a mnemonic device. I'm going to give you a mnemonic device. There's 4 variables. Watch this. Number of teeth, diameter, angular velocity. I will not give you the finger. I could. And torque. So number of teeth, diameter, angular velocity, and torque. Now here's the thing with the equation that's easy. All of the equations set up out, listen to this little rhyme, and I'm going to give credit where credit's due. All the equations set up out over in, except how fast you spin. All of the equations set up output over input, except for the rotational velocity. They all set up, and I'm going to go back and share now. Look at the equations. They all set up output over input, output over input, output over input, with the exception of how fast you spin your revolution. So all the equations set up out over in, except for how fast you spin. And I'm telling you right now, I didn't make that up. Cole Benvaugh, who's now a sophomore at University of Illinois Champaign. His sister, I think, is a senior and going to be a NASA systems engineer. Same thing, went to U of I Chicago. Both were robotics people and Science Olympiad people here. But Cole, when I had him as a sophomore, he came up with that. So I give credit to the student. I was trying to, just talk through things. And I love devices like that, but I got 4 variables. Okay, that's real easy. Number of teeth, diameter, RPM, rotational speed, and torque. They all set up out over in, except for rotational speed, how fast you spin. Okay, so it's helpful. Again, I'm not a person for rote memorization. I'm going to walk that walk. Will I give you formulas on, quizzes and stuff like that? Yeah. I want you to know how to set it up. And there's enough here. Like, so let's set these up. Let's look at these. Okay. What did we say? I counted the teeth already. So let's do one for the teeth. Okay. Output over input. I need to know what's the output, what's the input. I can't set my equation up. Oh, this is the output gear. I counted it. It's got 12 teeth. So it's 12 over the input gear has got 6 teeth. That's 6. Okay. Let's look at the diameter one. They're all equal to each other. Okay. They all set up the same way. And we can set them equal to each other. If I don't know the diameter of my input gear and I know 3 of the other variables, I can find it through math. Okay. Diameter, same thing. Okay, it gives it to me 4 here for the output. Well, 4 is going to go on the top. And then my input is 2. Well, input goes on the bottom. Easy. Okay, rotational speed. This is the only one where your input is on the top of the equation. Okay, only one. So now, okay, the rotational speed of the input gear goes on top. Oh, there it is. Here's my input gear, 40 RPM. That goes on the top. My output gear is 20 RPM. And look at that. What did I just say about rotational speeds? It's true. Smaller gears spinning faster. This one's going 40 times per minute. But look at the torque. Look at the torque. So this one, let's look at it. The bigger one goes half the speed, but look at that relationship. It's still, that factor is there of double. It's double in output torque, right? Nice mathematical relationship there. Half the rotational speed. This one's going 40, this one's going 20, but look at this. This one can generate twice the force. This big gear can generate 80 foot-pounds. So that last formula, same thing. Output, over input, and we're looking at torque. Those would have to be defined somewhere here or written in a word equation. You would have to have them given to you. You will not have to calculate for them. You will not have to calculate. Here's a force and a distance, calculate for torque. You won't have to do it. Okay, it wouldn't be hard, but okay. So those are our 4 variables. Those are our 4 equations. They set up real easy. And what we're going to do is use them and say like, hey, listen, what if in this equation I gave you an input, an output diameter and input diameter, and I gave you an output or an input velocity? Could you tell me the output velocity? Yeah, I would just set these equal to each other. Let me just do a quick drawing. Annotate. Here's what we're going to do without just putting simple, what we're going to do from now. We're not going to know. We're not going to have all our knowns. You're going to solve for the unknowns. So say this was the unknown. I didn't know that. Okay, I don't know the input. The output. Output RPM. It was never given to me. So solve for it. Given this equation, solve for it. Set up your equations and solve. Okay, well, what do I have? Okay, I got diameter and I got velocity. The whole thing says that I can set any 2 equal to each other. I could set torque equal to diameter. I could set diameter equal to rotational velocity. I could set rotational velocity equal to this. If they told me the gear ratio, if they said, hey, the gear ratio of the system is supposed to be 3-to-1, and you know the input size number of teeth is this, what would the number of output teeth be? Oh, okay, 2-to-1 is equal to X over 4. Whatever it may be. So any one of these 5, you can set equal to each other. Does not matter the orientation. You just got to set them up right. Okay, so important concept with that. Let's clear my drawing and let's move on. How are we doing on time? Okay, I'm not going to go too much longer because again, human attention span is only so long. Okay. Everybody with me? Holler if you're not. Scream, chat. I don't see anything in the chat. We're good. Okay. Pretty straightforward. I think it's much easier, especially once you've already done simple mechanisms, to understand this. Okay. All they're showing you there is all the units go away and we wind up just with a number that talks about gear ratio, right? Through math, all your variables cancel. Okay. This is exactly what I was showing, is that you could set them up any way. And we're asking, what is the gear ratio between gears A and B? Okay. All right. I got to look at it, but here's the problem with this one. Do they not? Okay, so a little bit of a problem in what you're seeing here, and I thought that they did, but they don't. They do not tell you in this word problem what is the input or the output. So it is assumed, okay, it is assumed that the input is starting here on the left. Okay, all of your math problems that you would get will always be defined. They will always say, what is the output of the input? If you don't know that, you cannot set up your equations properly, okay? And it might be in a word problem. We'll say, hey, given this drivetrain system, and it may say, well, yeah, pull, just by the way, gear A is the input. So then you know, oh, okay, gear A is the input to B, B is the input to C's output, C is the input to D's output. Okay, A to B, B to C, C to D. Okay, so that's all they're doing. What is the gear ratio between A and B? Okay, so let's set up the equation. Okay, gear ratio, and you wouldn't need to set this is equal to 1. All you'd have to do is out over N. That would give it to you. They're just saying, isn't gear ratio, right, synonymous with number of teeth? Isn't this another way? That's all they're saying is I can calculate gear ratio just using this variable. So don't overlook this. Okay, can I set number of teeth equal to diameter? Sure. Okay, but all we're doing is all I've got to work with here is teeth. So I'm going to calculate the gear ratio only using the teeth. Let's set it up. Out over N. We're using number of teeth. That is definitely an out over the N equation. It doesn't say, but this is the output. So so this is the input. Output over input. So the output in this case is B, A to B. B is the output. So that 12 comes on the top. 12 teeth goes on the top. This is the input. So my input says it goes there. And they did a little bit of simplification, but you wind up with that. It could be just 0.6. So the answer would be gear ratio is 0.6. Could you say 0.6 to 1? Yes. Okay, same thing. All right, so let's calculate it B to C. Fine, same thing, same formula, out over N. So B is the input to C's output. B inputs to C is the output. So we need to put C as the output on the top. C has 5 teeth. There goes 5 teeth on the top there. Output of B goes on, the input is B, goes on the bottom, and we wind up 0.42. Last one here. Whoops, go back. It's going to be C to D. Sorry, that little screen's covering C to D. So C is the input. That goes on the bottom. That's 5. Our output's the top, and we wind up 4 to 1. Okay, so different gear ratios with each of them, which should make sense. It's like, well, yeah, they should be different. They're all physically different in size and the number of teeth. Okay, so you should feel good about your answers. Look, should be right. Okay, and then what did we see? Let's see what else comparisons can we make. Really, where do we have this largest gear ratios from the smallest to the biggest? You know, these are comparable in size. They're not a big size difference here. And still pretty comparable, but here we got this really big difference from 5 to 12. We'll look at what it did to the gear ratio. Okay. This last gear is not going to spin very fast, but it's going to get a lot of work done. Okay. It could move some material. Okay. What is the total gear ratio? What is the total gear ratio? So how do we calculate total gear ratio? Well, all are doing is it's multiplied. We take the gear ratio of this one, we take the gear ratio of this one, we take the gear ratio of that one, and we multiply them. Okay, so pretty straightforward. Now, here's the curveball. You can calculate that over the entire system. Look at what they did. So I could calculate gear ratio 2 ways. I could look at the gear ratio, the independent relationship. There's a gear ratio here. There's a gear ratio here. There's a gear ratio here. Multiply them together, compound them, because this is a compound gear system. And I'm going to get that answer. But look how they got the same answer. All they did was focus on this relationship of output over input. And look what happened. They went from this input to that output. So that's the truth. A is ultimately outputting to D. So that's all they did. 20 over 20 gives you 1. So you got 2 different ways that you can calculate gear ratio in a compound machine for the overall system. For the overall system, there's 2 ways to calculate gear ratio for a compound system. We either multiply the individual gear ratios, or we can take the input to the output for the whole thing. Like most people are like, well, that's kind of dumb. I'm going to do the easy one, the input to the output for the whole thing. But it just lends credence to the fact that you can do it 2 different ways. There's many things in our life, okay? All right, it's 11:10. Let's kind of stop. Let me look. Let's see what's coming up next. They just show you some other examples, just others. Okay, I'm going to stop here. We're going to pick up. This is too much. We're going to overwhelm people. We have had 40 minutes. Okay. Stop sharing. Any questions? It's lowercase omega. Thank you. That's lowercase omega? Wow. I wonder why they use that.
It was in the speaker notes for the slideshow.
Oh, was it? See?
Yeah.
You know what? So here's the thing, Jafar. I've been teaching this class for 7 years. I don't read the speaker notes anymore. I read them my first year. And I don't remember everything. So it's good, right? Multiple exposures. The human brain learns. No, we did not have class yesterday, guys. That were popping in yesterday. A couple of people have asked in the chat, was there class yesterday? No. Remember, Mondays are going to be, well, I said they were going to be optional, but if you popped in late, I'm going to pop in for Mondays real quick. If you don't want to pop in Mondays, you don't have to. If you want to, I will be a happy smiling face and I will be there every Monday, albeit if it's for 2 minutes, okay? All right, if there's no questions, which is good, and it's hopefully there are, but hopefully that, to me, I'm going to take that as understanding that you guys are like not intimidated and I'm doing a relatively okay, not shitty job, pardon me, teaching, and you get what I'm saying. It's in the stream, so let's jump over. Somebody is asking where's the slideshow. The slideshow is in the actual stream. So if we escape out of this, stop sharing. I do want to share this. So if I go to classroom right here in the slide, so I posted it the other day, posted it at the end of last week. So there's that slide. So all I'm going to say for, and I'm going to take a look at the chat again, it's posted in the stream. I'm not going to give you any work for Thursday. I want to cover the rest of this. And then I'm going to cover, I'll probably talk for, when we meet Thursday, I'll probably talk for about 10 minutes and kick you off onto your problems real quick. We'll look at some of the ways that we compound gear ratios and multiple systems. If I have a wheel and axle with, what happens if we mix a wheel and axle, a simple mechanism with a drivetrain system? So we'll further our knowledge with that a little bit, and I'll give you a couple practice problems, and that'll be our week. And just as an on just looking down the road, we will quiz next week. We'll wrap this up by like next Tuesday, probably next Thursday. We'll have a very simple quiz on simple mechanisms and gear ratios. Very, very reflective of what you've seen. Okay, but I do want to talk about the screw on Thursday as well, because it's an important simple mechanism, and it's just different variables. So you do not have homework today. I'm just trying to answer the questions in the chat. You do not have homework today. Let me stop this and just make sure I can see the chat better and I'm answering it. No, you do not have homework today. Just to kind of, if you want to look at that PowerPoint and go ahead and look at it. No, I just don't feel comfortable. We've covered enough and seen enough practice problems. So we'll see a couple more practice problems. Review that, look at it if you want tomorrow. Thursday, I'll give a little bit more instruction for about 10 minutes. And then we'll probably have the rest of the class to work on stuff. And I'll just be there if you need it for questions. You'll finish that for Friday. And then when we see each other again on Tuesday, we'll review it real quick, because I think the simple mechanisms really set a good foundation for us understanding gear ratio. Like, okay, that's pretty straightforward. I get it. Okay. And that's it. So just to review, drivetrain systems, they get work done for us, but we got that whole other variable of gear ratio, right? We get work done, but we're no longer concerned with mechanical advantage. We're concerned with this new concept of gear ratio, and the greater the gear ratio is, the better, okay, generally speaking. There's robotics. A couple of people in the chat are asking about robotics. That's going to be posting and sending. We'll do, it'll be Wednesday at 1:30. I will post a link and do all that stuff. I will post something in Classroom, okay, but I'll send out personal emails. I'm just answering a couple different questions. Any other questions? Anything I didn't answer? Anybody want to yell at me, Risto? Yes, no, good. Okay, I'm going to hang out a few minutes.
action. The Agile Falcons plays down a payload. Oh, it sticks, but it does not leave that red top.
Take the test off. 2 minutes, 5 seconds.
Oh, the wheels push down that solar panel already. And staying goes for the Astro Falcons. That's a big point scored for both teams. 45 seconds down. What will they do? Remaining 1 minute 45. The robot pulls the down, but in a weird fashion.
Are you guys ready for the next one? Is it worth it?
Let the robot do its work, and then we just have to pray that they can. They have to rock it. Don't fail me. They have to do something else.
Align it. 5, 4, 3,
Not enough turn.
Yeah, it'll be fine. It's just a line. See, but get ready for the next
Throw
one.
walls for the
I want to see some beauty here on the kick.
This works. Let's see what they can do next. Very close call. 4.
Come on, guys, you can do it. You can do it.
Working with top Tigers.
Hello, hi there. This is a fidget spinner I made today. It is like made out of Battleship chips. So you know those red and white ones you used to play with Battleship in Battleship the game. And then I used the bearing from another fidget spinner, broke the other fidget spinner and used the main bearing and then attached the Battleship chips to this bearing with Gorilla Glue, and it went well. All I have to do is just like clear all the glue, and yeah, here it works really well.
Hello guys, my name is Hello guys, my name is Shri. Today I'm going to show you how
Hello guys. By the title of this video, you guys can probably tell that I'm going to be teaching you guys how to get infinity on a calculator. So what you're going to need is any search engine and just type in calculator.
Hello guys, my name is
Hello everybody. So this is Shripad, and over here is a Rohan. We're the Sons of Hephaestus. Subscribe. If we get over 10,000 likes and 10,000 subscribers, we're gonna make a funny video of a car going down the stairs that we created with a bunch of funny little kids in it. Also, please hit the notification bell so that way you don't miss out on any videos that we post. Now, with the pep talk done, let's get this thing started. 3, 2, lift off! Oh, nice jackpot! That one went down in like 1 leap. And, oh, I mean, with the dance. Okay. Downstairs. And it goes down, I think. Let's check. Let's check. Where is it? Oh, it's under the table. Nice, let's do it. Let's go, boys. Oh, cousin of Hephaestus. Okay, and that's it for the car going down the stairs.
Hello, I'm John Thorne from Thorny Motorsport, and this little short video, even for us, is about literally the longevity and a good way of demonstrating that the McLaren model car is actually pretty good. Now, in the example of 12, but we haven't seen any lower than that until last week. Now, it was a silver car, coupe, obviously a swipe door car, and we took a time to call McLaren up and to see whereabouts the build order were in these cars. And
Hi, this is me. My name's Shri, and this is a Rohan. We're the Sons of Hephaestus. Okay, so this, I made a creation. This balloon. Okay. Oh yeah!
been the top in one or two areas, but consistently demonstrated all the core values, robot design, project presentation qualities that are necessary for a champion. This team looked to help astronauts in space during downtime. If it ever becomes boring in space, this team's solution will keep things lively. This team proved that birds can fly in space. Team 4-2-2-6.
So when you say I'm like, nah, dude, he's way more than that. He's way more than that. You see, I don't have the luxury to worry about freaking. I did it. To me, Trump is a freaking godsend. To me, Trump is what is life. To me, Trump is a second chance. Sorry about that if you didn't hear me. To me, Trump is a second chance. So when you say I'm like, nah, dude, he's way more than that. He's way more than that. You see, I don't have the luxury to worry about freaking Roe versus Wade. I don't have the luxury to worry about that. I'm too busy trying to keep my family fed to think about that. And for the first goddamn time in my life, I actually see a way out. I see a way out. Something I've never seen before. I see a way out, man. And just that little bit of hope is enough for me to have a fire in my belly, powerful to freaking charge the goddamn world, man. I'm ready to take over, but if Biden
you